Okay. So this doesn't sound so bad. I mean, just exponential and logarithmic functions. Not that big a deal.
Doesn't sound so bad means it's gonna be bad.
We're talking. You got to learn how to do 4 derivatives.
Just screw with your mind is nothing.
Yeah.
Yep.
Okay. We want to do exponential functions, which are just a number to a variable power, like 2 to the x, 5 to the x, 8 to the x.
Well, this is where we're going to figure out how.
We want to do e to the x. E to the x is the easiest derivative you'll ever learn.
0.
Almost that easy. X to the x, which, yeah, that one takes an actual method to do. And then, of course, we want to get derivatives of natural log of x.
Dual color.
Okay. You will not, well, you'll see some regular logs, log base 7, log base 2, but we're going to convert them into natural logs to do the derivative. You will never, you can't actually do the derivative of a regular logarithm.
Caleb, just out of curiosity, was that your least featured game for Peyton Gould?
Okay. Bailey, we just talked through the proof of why natural log of x's derivative is 1 over x. If you really want to see that proof, I'll be happy to explain it to you, but we didn't record all that. What we have just discovered is that the derivative of natural log of x is the nice little simple 1 over x. So it actually is quite an easy derivative. And Alex was just complaining, okay, well, what if it's got some nasty stuff in it, so we'll be nasty. Suppose it's got x squared minus 3x inside that natural log.
Is it 1 over x squared minus 3?
Isaac thinks it's 1 over that whole quantity.
Don't say my name. I don't want this out on the internet.
You're right. You want it out on the internet. So, yeah, it's just do the derivative. You do 1 over whatever's inside the natural log. So it'll be 1 over all of that. But because it has a quantity inside it, you're doing what rule?
Chain rule.
Chain rule. So now you have to times by the derivative of the inside, which would be a simple 2x minus 3. Now, the downside is you have to simplify these some. Yeah, exactly. I mean, I can't cancel anything. There's nothing. Yes, I could pull an x out of the bottom, but it's not going to cancel with anything. So, yes, but they are, because of what happens with a lot of these, they are going to ask you to do some simplifying because sometimes a lot of stuff will cancel. So, you get to simplify some on those. Yay! Look excited. So, suppose, let's make it a little more fun. Suppose our fun natural log is inside, say, a trig function. And I want to do this derivative, the secant of the natural log of x cubed. Okay, so, and of course I picked the mean trig function to do a derivative of. What's the derivative of secant? Secant tangent. So secant of what? Yeah, the secant of the natural log of x cubed. Tangent of all that stuff. Okay, this is one of those, go back and keep your eye on the original. You did the derivative of secant. Now you're doing derivative of the natural log, which would be what? 1 over x cubed times the derivative inside of that. The derivative of x cubed is 3x squared. And you'll notice then, this is why they will have you simplify these. Particularly if it's a single variable, what's going to happen right there with those x's? X squared and is going to cancel with this, and I'm going to be down to just x to the first power. So it's just 3 over x, yes. Consequently, they will typically pull that 3 over x to the front and say it's 3 over x times the secant of all this stuff. It's okay if you leave it out back, yes. They'll generally pull it to the front. So, natural log, not bad, right? That's okay. All right. So, suppose I give you a log that's not natural. What do you do? You complain and whine. Yes, that's going to be a good option.
For performance enhancing drugs. And then you take away all the records.
Okay. Well, I can't remember if I said this to you last year because with the changes they made in calculator operating systems today, used to be to do a log base 8 on your calculators, you had to know this formula called the change of base formula. Since they've updated calculators, even the 84s and the Inspires, you can type in whatever base number you want. So,
Cross out 5A then or
cross out 5A. What's the change of base? No, because now you have to know it in order to do your derivative.
What must be considered when finding the domain of a natural?
So no, you can't get rid of it. You have to learn it now, which is so incredibly simple. Basically, what it says, in our case, we want to change them to natural logs. This formula actually works with any, you can change it to any base log you want. And it comes from actually working out logs and using the plug rule. That's how you get this formula. But essentially, if we want to change it to natural logs, you're going to do the natural log of A, the argument of your, divided by the natural log of the base. Okay, I always remember, A, argument goes to the attic. Base goes to the basement. Attic, basement. Argument on top, base on bottom. So therefore, before you can do the derivative of this log base 8, you have to convert it to natural logs because we only do derivatives of natural logs. So, according to that formula, what would I change this to? Nat
3x to the 7
over natural log of 8. Yes. And then you do the derivative of that function. But I also have to get you to realize something. Does this require a quotient rule?
Yeah, it's on the second part.
Is the bottom... Your feeling is correct. Does the bottom have a variable?
No.
Bottom's natural log of 8. It's just a number. That's just like having a 3 on the bottom. This is not a quotient rule. In fact, what I'm going to tell you to do with these is I'm going to tell you to treat it like 1 over natural log of 8. It's just a fraction sitting there. And all you're doing the derivative of is the natural log of 3x to the 7th. That's just a constant number. It does nothing but sit there. So when you go to do your derivative, constant numbers, if you're doing product rule, if you were doing their derivative. But when we do derivative of 3x to the 7th, you all will tell me that's 21x to the 6th. But isn't that also 3 times the derivative of x to the 7th, 7x to the 6th? So the 3 is just sitting there. Numbers that are multiplied just sit there and multiply. They don't go away. So you can actually just leave this 1 over natural log of 8. Just let it sit in front. Don't do anything with it. It's just a number. Now do derivative of the natural log of 3x to the 7th.
Is your board grown?
It grew again.
But like more assignments.
Yeah. So natural log of 3x to the 7th becomes 1 over what? 3x to the 7th. Don't do the derivative. Always have people want to do the derivative there. Times, now do the derivative inside, 21x to the 6th. Will that simplify?
Yeah.
What will reduce? 3 and 21 will become 7. And x to the 6 will cancel in, leave us 1 over x. So in the end, you still have a 7 on top. If it's single variable, yeah. If you have quantities, not so much. But if it's single variable, yeah, it always cancels like this. So it actually turns out kind of cool. And yes, they'll put the x. They usually put logs at the end of the list of terms.
Funky looking 8, but 8 has the heart on top.
Because if you wrote it the other way, if you wrote it like that, what's it look like?
The natural log of 8.
Looks like the natural log of 8. If you're going to write it that way, you'd have to put natural log of 8 in parentheses to show that x is not in the log. So that's why we usually put the variable first. So I prefer you didn't do it that way. Okay, that's log. Woo! Yay. now that we know not logs, we can do exponential functions. Notice, this is one time I'm doing in reverse. Usually we have to do exponential functions to get logs. This time I need logs to get exponential function rules for you. Mm-hmm. Okay. And for some reason, when I write this, we forget this rule. This is the #1 most forgotten rule ever. Okay. The calc books write it as a to the x. We always wrote it, in algebra books they write it as b to the x, a base number to a variable power. A is a number. And those restrictions. Okay, because they said way back when they created exponential functions, they said we were always going to have positive bases.
Oh, you're talking about that.
And they can't be 1 because a base of 1 to a power just stays 1 when you take it to a power. So base numbers always have to be positive. And that's the same rules we've always defined them to be. Okay. Here's where you're not going to love me so much for a moment. Mm-hmm.
What if A is 1 and X is 0?
A can't be 1.
So what if back then I come up and I didn't like what it was?
We'll deal with 1 to infinity 2 classes from now. It's coming, don't worry.
Y'all are all lucky I wasn't back then.
Okay, to get this one, to get you the rule for why this derivative is what it is, and this is actually a handy method. You're going to think I'm crazy, but to come up with that derivative, I need to get x down out of the power. What's the only way to get x down? Log. So I'm going to log both sides for a moment, because that would let me pull x down front of my logarithm. Okay. Now I want to do the derivative. But now that I have nat logs on it, I have natural log of y, this is no longer an explicit function. It is now an implicit function. So we're going to get this derivative by doing implicit differentiation. So what's the derivative of natural log of y? 1 over y. Implicit, you did the derivative of y, dy over dx. Okay, now here, remember, natural log of a is a number. So that's like saying I have 4x. That's a number times x. What do you get when you do the derivative of a number times x? What's the derivative of 4x? 4. Derivative of 10x is 10. So the derivative of this, of natural log of a, x, is natural log of a. Do I need a dy over dx on it? Nope. Okay. I need to solve for dy over dx now. How do I? Multiply y over there, which I'm going to throw in front of that natural log, so I don't confuse you. Okay, but I need my answer in all x's. If I want to do derivatives of something to an x power, I need x's in this answer. So what do I put back in place of y? What did I know y was equal to? A to the x at the beginning. So I end up with a to the x times the natural log of a. That's not cheating. It's using your mathematical opportunity.
That's what all criminals say. I was just taking an opportunity.
So in other words, you need to process what this is saying. If you're doing the derivative of a number to a power, it's just that same exponential function times the natural log of its base. That's all this rule is out to do for you. So if I said, what's the derivative of 5 to the x? What would you tell me? Times the natural log of 5. And if I say, what's the derivative of 17 to the x? It's the derivative, it's itself times the natural log of that base. So the derivative is itself. That's kind of cool. But now, here's the coolest one of all. If that's true, what's the derivative of e to the x? It's itself times natural log of e, which is 1, isn't it? Because that cancels. So the derivative of e to the x is e to the x. It's itself. It is so, I think it's the easiest derivative because it's itself. You love derivatives of e to the x. They're your best friend. So I should have left myself some space up there. I'm going to do a slight movement here. No, I'm not. I missed. Okay, dude. Come on, give me a move tool. Because now I want to rewrite up here so I can have my rules together. The derivative of e to the x is e to the x. And those two buddies are our good friends. Ooh, I should stop.